Last talk in the session, this will be about near log convexity of measured heat in discrete time and consequences. And the talk will be by Mert Saulo.
Hi, I will be talking about near log convexity of measured heat, and let me tell you what I mean by that. Suppose we have a finite set omega and a positive unit vector which is showing some initial configuration of a positive quantity like heat or particles, and we have suppose we have a symmetric matrix, say substochastic, on the same space omega, and we let u evolve according to s in discrete time steps. In particular, if we started from u at integer time step t, we end up with ut, which is s raised to the power of t times u. So we're interested in heat, let's say, contained in a certain region given by another vector v, and how does this quantity change over time as a function of t. So for normalization, let's assume that both u and v are positive unit vectors. And so we want to say something about mt that holds true for any s, u, and v that satisfies the symmetry and positivity and magnitude constraints that we mentioned earlier. I mean, from here, we can already see that, let's say, if the circle denotes the region that we are interested in, we can already see that it's not necessarily monotone. I mean, it starts small and a lot of mass comes in, but soon enough that mass will spread out evenly and then it will go back down again. So we can already see that MT is not necessarily monotone. And what can we say about MT? So in 1966, Blakely and Dixon, and later in 82, Erdős and Simonovitz conjectured the following. They study almost the same thing, except that in their case, u and v are the same vectors. They say that if we take two integers, k being the larger one, of the same parity, mk to the power of 1 over k is no smaller than mt to the power of 1 over t. So namely, this is another way of saying that mt to the power of 1 over t is monotone if we increment the input parameter 2 by 2. So first, our first result is that we show the conjecture is true even in our more general setting where u and v are allowed to be different. And furthermore, we characterize the equality conditions. So notice that, I mean, this is a monotonicity statement, so we can prove the one step and the rest follows. The most difficult part is proving this. Once you have this, we can iterate and get the entire statement. And moreover, we show that something stronger actually holds. We can improve this by a factor of t unless we have this sort of more conventional convexity statement. So let's rephrase this, putting this or else into a min. That's exactly what we get. So this is essentially saying that we have log convexity, except that when the ratio on the right-hand side is too large, we have to truncate it. So why do we care? So using these are actually, it turns out, tightly related to questions in complexity theory. Using theorem 2, black box, we obtain the following results. Randomized communication complexity of the K-Hamming distance problem is omega of k log k. And furthermore, we can show, using a similar argument, that any parity decision tree, randomized or not, deciding the K-Hamming weight problem needs to have size exponential in k log k. And through well-known reductions, this also shows that any property tester for k linearity requires k log k, and similarly, for k juntas, k DNFs, size k decision trees, and so on. So let me tell you, in this talk, I will only focus on the communication complexity result. And so let's define the k Hamming distance problem. So we have two players, and each of them receives an n-bit string with the promise that their Hamming distance is either k minus 2 or k. And they work together, meaning intentionally, but they don't see their inputs, and to determine which is the case, whether their Hamming distance is k minus 2 or k. So there is a trivial upper bound of k log k, which is obtained as follows. I mean, roughly, Alice sends a linear sketch of her string, where the sketch is obtained by an MDS matrix, which is like the parity check matrix of a linear correcting code. And with this, Bob can actually recover, I mean, under this promise that the Hamming distance was small, and along with this sketch, Bob can recover x in entirety. And having x and y next to each other, he can clearly count the number of differences and decide which is the case. So by well-known bounds of Warshamov from 50s, we need just k log n over k bits to do this. So the next trick is that, I mean, if we just suppose we have n coordinates, but we can hash these into 10k squared buckets, and with good probability, no two differences will collide. They will all end up in different buckets, so we won't really change the result with all but constant probability. So we first do this and then use the protocol above. Now n being k squared, we get the result k log k. So highly related problem, just to contrast, is the k disjointness problem, where two players get a k subset of 1 through n, and they are required to determine whether their sets intersect. So notice that this is a special case of 2k Hamming distance problem, and with the promise now that the strings are also Hamming weight, very low Hamming weight. So because of this, if we have a protocol for the k Hamming distance, we can solve instances of k over 2 disjointness problem. So here are the known results, and because of the relation that I mentioned, every upper bound for the Hamming distance problem applies below, and every lower bound for the disjointness applies above. So there's a omega of k lower bound from the usual disjointness problem due to Schnitger and Kalyana-Sundaram. And yeah, there were some results for one-round protocols, and for disjointness later on, it was shown that if you have an R-round protocol, a k log iterated R times k lower bound applies. So this, along with the work of Blaise, Brody, and Ghazi, were the strongest lower bounds prior to this work applying to the Hamming distance problem. So here we show that the trivial upper bound that we briefly looked at is actually tight. That was a one-round protocol with minimal sophistication, and no matter how many rounds you have, you cannot improve on this up to constant factors, except maybe for a factor of 8. So our proof of theorem 1 is fairly straightforward. So let me try to explain that briefly. So let's recall theorem 1. We had a symmetric matrix S, and with non-negative entries, and two unit non-negative vectors u and v. And for integers k and t of the same parity, we claimed the following. So we can scale S as needed so that we can make it substochastic, and in fact, by completion, you can make it stochastic without loss of generality. And so now we had u and v, which were unit vectors, but the thing is that we will see them as probability measures by scaling. And we view the statement as a statement about random walks on omega that start from a new state that we introduced as the start state and end up in yet another auxiliary state we introduced f, where the first step is taken according to the mu distribution and the last step is taken according to the new distribution, as I will tell next. So we define a random walk ft as follows. We start at S, which was this new state that we introduced, and move into one of the states in omega, which are integers 1 through n, with probability mu of x. And after that, for t time steps, the random walk moves according to S. Recall S was a stochastic matrix, so it describes a random walk on omega. And at time step t, we move to f with probability mu of x and just go to a fixed arbitrary state in omega, let's say with probability 1 minus nu of x. So likewise, we define a backwards walk that starts from the final state this time and proceeds backwards in time. It starts with time step t plus 1, goes until minus 1. And the thing is that we move from f to a state in omega according to the probability distribution nu this time. And when we are at time step 0, we move to the start state with probability mu of x, and with probability 1 minus mu of x, we stay in omega somewhere. So, I mean, these are, let's go through what we have defined. The forward walk f starts from the start state, and the probability that the forward walk ends up in the final state is this quantity that we are really interested in. I mean, mu times s to the t is the distribution of the Walker after t discrete time steps. And for each of the states that we end up with, we go to the final state with probability nu of x, so that's why we have the inner product there. And for the backwards walk, exactly the same. You start from f and then do the walk backwards and then go to s with probability of mu of that state. So the walk x is obtained by taking the forward walk and conditioning that we end up with the final state. And assume that that probability was not 0, which is the quantity that we want to study. One can see that under this conditioning, the walk is still Markovian. This is some standard fact. And also, the backward walk conditioned on reaching the start state is this walk also. So the idea is that now we will create a random walk that will span t plus 2 time steps and still will be not too divergent from the unconditioned walk. So to do that, we pick a random time step between 1 and t, and at that time step j, we introduce a spurious, let's say we go backwards in time once and then go forward. So this way we introduce 2 more steps and then continue from where we are left, as in we are doing the x walk again. This way we obtain a length t plus 2 random walk z that ends up in f just like x. Here I say random walk, but it's actually a random walk when we condition on a particular j, but the mixture could be not a random walk. So intuitively, I mean, the walks back and forth that we introduced, on average, should add 2 over t times the divergence of x from f. And if we can prove this formally, that's essentially what we want to prove. So, okay, let's take a look at KL divergence. That's what we are going to use to analyze these. So for 2 distributions, mu and nu, KL divergence is just the log ratios of the distribution sampled according to the first one. And we can extend the definition to apply to random variables too. So an important thing that we will be using is that if we take a random variable and condition on an event happening with probability p, then the condition random variable diverges from the original one by a log of 1 over p bits. So just using this, we can understand how much x diverges from the unconditioned random walks forward and backward walks, and which is exactly the log of the probability that the walker starts from S and reaches the final state F. So now let's do the walk Z more formally. These are the properties that we want. So we pick integer j uniformly at random, and in the time steps up until j, we walk just like x, and at time step j, we walk according to the reversed x, what x would do if we were traversing it backwards in time. And next, for the upcoming walks, the steps, we just imitate x exactly. So here's a pictorial description. The red one is the x walk. It just goes back forward in time for t time steps. But in Z, we pick a random time step, and at that time step, we sample a predecessor to the current state according to x walk. And then from there, we just keep doing the x walk forward in time. So chain rule, the KL divergence satisfies a chain rule, which is particularly convenient here because everything's Markovian and we don't have to condition except for the last previous step. So now we can, for any fixed j, just write down the divergence of z condition on j from the unconditioned walk. And the idea here is that we can take out the reversal and going forward in time and analyze them separately. So what we end up is that we can just think about every reversal for different choices of j. We can stitch them together to obtain a new backward walk. And likewise, we can stitch together all the spurious forward walks to obtain a new forward walk. And just carrying out the analysis, that's exactly what we get. Except that we don't have the divergences accounted for when we walk into omega from S, and likewise we move out of omega to the final state F. These we handle separately. And it turns out when we can lower bound these things exactly by the 2 norm of mu and nu, and if you remember how we obtain mu and nu from u and v, this is exactly the factor we lost, which makes up for that factor. And just plugging everything in, that's what we get. So this is the proof of theorem 1, which answers a conjecture of Blakely and Dixon, and also Erdős and Simonovitz. And yeah, thank you.
Questions?
So how do you connect the randomness dispersion walk to communication?
So the connection is the following. Just in the communication setting, just take the standard random walk on the hypercube. If you do that for k minus 2 time steps, you will most likely, if n is large enough, you will get a string that is of Hamming distance k minus 2. But if you do that for k time steps, you will get a string that is of Hamming distance k. So sort of that Hamming distance becomes a time in the analogy. And you had it? Okay.
Any further questions? All right, let's thank the speaker and all the speakers in the session.